All right, well, good morning. My name is Tommy Gober, N5DUX. I live down in Houston, Texas area in the Woodlands. This is Larry Kendall, K6NDL, and you're in Apple Valley, California, just outside of the LA area. Today we're going to be talking a little bit about how you can demonstrate some radio principles to some of the newcomers, maybe strengthen your own understanding of how radio works. And some of the concepts that we're going to be covering today are topics that we use in the ARRL's Teacher Institute. That's what brings Larry and I together. Each summer we teach a one-week workshop that's put on through donations by the American Radio Relay League through the Teachers Institute. And the education workshops that we do, we have teachers come from all 50 states. They work for 1 week each summer, covering basics of radio electronics, basics of programming, and basic soldering skills and so forth. So that's a free workshop that any teacher in the country can use and get into. So some of these introductory concepts and projects that we've got are simple, easy to build for the most part, and don't require a very, very deep radio understanding of what's going on, but that's one of the things that we like is it's introductory. It's stuff that you've probably seen maybe before, and it's not something that's necessarily radio specific. So the first thing we're going to start off with is I'm going to reach back here. I'm going to grab we're going to do the pipes, and can you get me a couple of magnets? You got these magnets? Okay, so these are super secret selective pipes. These are made specifically for amateur radio operators. You can only buy, no, I'm just kidding. Standard PVC pipe, aluminum conduit, and copper pipe.
Yeah, all available at Lowe's or Home Depot, not a plug.
And so yeah, any big box store. Now, Larry, I did have one question that somebody came by the ARRL booth earlier, asked me a question on this. So the PVC, I think we all know what that's good for. Copper pipe.
Plumbing.
Pretty standard. Where do you get aluminum pipe and what do they use it for, do you know?
Crafts and just special projects. They just sell it in usually 4 to 2 foot multiple lengths.
Okay.
2 foot, 4 foot, 6 foot, 8 foot. There's catalogs you can order it and have it sent to your home. But and if you have a metal supplier, we used to have a couple of metal supplier. I could just go in and ask for whatever diameter I wanted. But it's probably most effective if you can find 3 pipes that have the same inside diameter and the same wall thickness, but that's not always possible. The idea works, it's just kind of a better demonstration if you can get pretty close to the same.
So, and by the way, I'm gonna try and speak off the mic, is that okay? We're probably gonna be moving around a little bit. Okay, so next thing we've got is a standard neodymium magnet, so a rare earth magnet, pretty strong. But as I mentioned, we've got aluminum and copper. Now, those are non-ferrous, meaning that the magnet's not going to stick to those, right? It's not sticking anything here, though they do stick to each other in the case when we pack these around, and they'll definitely stick to your credit card magnetic strips. So they don't actually stick, they just wipe it out. So if we drop it through the PVC pipe, what's going to happen? It's going to fall through, and of course it falls right through. Why? Because there's nothing going on. If we put it...
What's pulling it through?
Gravity, okay, so we got gravity falling through, and of course I'm going to roll it on the ground there. If we move over to the aluminum and we drop it through there, how fast do you think it's going to go through there? If I drop it through, let's time it real quick. You don't have to count or anything like that. You probably don't have time. If I drop it through here, it comes through pretty quick. Now if we put it through here, I'm going to try and catch it down here. Is it stuck? It's coming through. There it is. Is that weird? What's happening with that? Let's try it again. Okay, so 1 1,000, 2 1,000, 3 1,000, 4 1,000, 5.
Wow. It's really impressive with a full stick of.
You get the longer stick you get.
A ladder and.
So that's going through aluminum. Now, what's going on here is as the magnet falls through the pipe, it's generating electron flow. As electrons move, they generate a magnetic field. As that magnetic field moves, it induces electrons to move. As those electrons move, magnetic field. We got electrons moving and we've got magnetism. So putting those two things together, we end up with electromagnetism. Now that's something that is covered in the technician license exam. So near every ham knows this concept, but how much do you really know it? And so it's this play back and forth that's going on. As the magnet is falling, it's creating a small electric current, which creates a small magnetic field, which keeps the magnet from falling, or slows the magnet from falling. And as the magnet slowly falls down, it creates that magnetic field. And so it's constantly resisting its movement, or it's falling through that pipe. So gravity's still pulling it down, but that magnetic field is slowing its descent. That's through aluminum.
Why can't it be so, if you had a really strong magnet, like a really thick pipe, why could it never stop though? Why could it never be so strong that it would just stop that magnet?
Well, I think it's because...
What is it that generates the the electrical current? What kind of magnetic field?
Well, it's an opposing magnetic field. I was thinking that if it was to stop...
Moving.
Oh yeah, it's the moving magnetic field.
It's a change in the magnetic field that's generating the electron flow, not just the magnetic field.
So I was going to say, if it stopped, well, there's no electrons moving, so those electrons aren't moving a magnetic field to stop it, to slow it down. So that's going through the aluminum pipe, and I'll drop it one more time, and we're just going to let it fall all the way through. So the next pipe of this little triad that we have is a copper pipe. So copper, what do you know about copper in its relation to aluminum? Which is a better conductor, which is a maybe a little bit slower conductor? So copper is actually a little bit better conductor. So what do you think that's going to do? Is that going to speed up our magnet, or is that going to make it slower than the aluminum if it's a better conductor?
It's going to be faster.
You think it's going to be faster? Okay, so let's put it in here. There we go. So it's slightly slower. Now I mentioned earlier that we have some friends that we were recording this for, so that as they're playing this video, they may be able to go back and actually time and find out when does it start and when does it stop and tell us. But if you notice, it goes a little bit slower than the aluminum. It's slightly better conductor. Yep.
The thing that probably threw me off was that, when you have copper wire, which is in your coaxial cable, how fast radio communications are when you hit that transmit button and the person on the other side of the ocean here, it's just like that.
It seems instantaneous. Yeah. So she was saying that the copper wire in your feed line, how when you transmit through that, it seems to be instantaneous, that it instantaneously excites the receiver. But as we might know, that through physics, we're traveling at near the speed of light going through the feed line. It's going near the speed of light going through the atmosphere. And so for us very slow humans, it seems instantaneous to us, but in the world of physics, there's actually a delay in there. So the further you go, the longer that delay is.
By the way, if anybody would like to donate a silver pipe, it'll travel even slower.
Yeah, so we'd love if anyone wants to send us...
Silver's the best conductor. Problem is it tarnishes.
And
it's expensive.
It's a little pricey, I've heard. Not a lot of silver pipe in the world, is there? So what's going on? Why is the copper going a little bit slower? If it's a better conductor, it is allowing more electrons to move, which generates a stronger magnetic field. And that stronger magnetic field resists the magnet falling that much more. So these are just three simple pipes that, they're easy to source. That's why we chose these three particular ones. The length is completely arbitrary. You can cut it any length you want. And the reason we have them zip tied together is because we travel quite a bit with them. And so it just keeps them nice and handy to keep together. That way you don't have sticks of copper and aluminum going everywhere. But this is a great way to talk about magnets moving and creating a electric field. And that electric field then generates that magnetic field and vice versa. That relationship going back and forth really illuminates that.
When I'm doing this with students, it gives you the opportunity to just leave it as a wide open question for as long as you have or as long as you want. And they can suggest, well, what if you do this? What if you have more magnets? What if you drop 2 magnets, 3 magnets, 4 magnets? And it becomes just this experimental test bed.
All sorts of different variables.
That they can test all these different variables and try to understand. And by all means, have them look through the tube and watch it. The first thing they're going to say is, there's something in the tube. There's something rubbing against it, preventing it from falling. Well, you watch. Does it look like it's rubbing as it falls down? No, it looks like it's hovering, like it's floating down. So
those of you that are here with us today, if you want to, come up here at the end, look through it when we finish up. Folks that are viewing this online, definitely check out YouTube videos. It shows it actually falling down through that pipe, and it just appears to just be hovering as it comes down through there. So definitely check that out when you get a chance.
This was a little variation on it. I do this with both a steel ball bearing and an equal size magnetic sphere. And this was off a sign, a little metal sign that was jammed in our yard from our security company that broke off. And you can see so you can see, I mean, you can even do it vertically. Now if you tip it over, it's not, you say, oh, it's magnetic, so if I tip it over, it's just going to stay in there, right? Oh, I did it in the wrong spot. It's a little pinched right here. Okay. Oh, it's pinched there too. Let's try it down here. Come on. It's squeezed together. I guess that ball is bigger than the other one. Anyway, there's nothing holding it in there. It's not held magnetically. It's just that magnetic field.
I thought you said it was going to fall if you turned it over.
Oh, it will. It will fall out. Somehow this got pinched.
I know, that's why I called it.
Yeah, it should fall out.
So
Not doing it.
this is a really cool demonstration because you can actually see it going through, and you see that there's nothing impeding its movement through there other than that invisible magnetism that's in there.
And you can modify the tubes in different ways, see how that affects it. Tubes in tubes. There's a lot of different variations on that thing.
So we've got electrons moving because we've excited them with magnets, or you can excite them through any kind of other electrical source. Your wall power, any kind of solar or battery power, any chemical reaction that you can get electrons moving, then through our radios, then we can excite a magnetic field, and that's how the magnetic loop works, right? If you've ever heard of a magnetic loop, that's a loop style antenna rather than a dipole or any kind of variation on that. So as we get electrons moving, then we can get magnetic fields induced, and if we put more power, if we get more electrons moving, then we get stronger magnetic fields, which moves more electrons and back and forth all the way to the receiver. You mentioned earlier that it seems almost instantaneous that we transmit a signal and the receiver hears that. So what I've got up here, this is another super secret, highly specialized 2 lengths of scrap Romex power wire that I from a project I was doing at my house. I cut these to the length of a 70 centimeter dipole, and it's just I have a black wire on this side and a white wire on this side. I'm holding a wooden dowel rod, and I have electrician's tape just holding those 2 dipole elements in place. So they're stiff wire, and in the very center of a dipole, that basically what you think is the feed point, I actually have a small light bulb in here. It's not an LED bulb. LEDs won't work. I need a standard light bulb, an incandescent light bulb. So I have a small incandescent flashlight bulb on here, and that's soldered to those 2 elements on the dipole. So this is basically a receiver that is not an audio receiver. It's going to receive electrons from basically the atmosphere as I transmit, or as Larry transmits, and that's going to then excite the electrons in here, and as it transmits, it's going to excite the magnetism. It's going to have electromagnetism exchange, excite the electrons in here, and then that's going to create enough voltage that we should hope to light up the light bulb. It's going to be kind of dim, so those of you in the back, you may not be able to see this, but what frequency are you on?
436,790.
436,790. So he's in the 70 centimeter band, going to transmit FM, which is just basically full power. And as I get this closer to it, now this is obviously, this is not a super sensitive light bulb, right? I need to get closer to him as he keys it up. And as I get closer and closer, it's just starting to glow. It's very hard to see from where you guys are, but it starts to glow a little bit brighter, until it gets really, really bright up close to it. And as I get further away, you can see that it starts to dim and fade away. Can you see how bright it is right here? So it's a kind of a hard thing to see from a distance, but as we get closer or further away from that, you can see that it's really strong. Now in radio, whenever you're near a station, it's really, really strong. they come around, they sound really, really loud, and there's no or very little interference between you and them if there's any kind of natural noise, any kind of QRN or anything. And that's because you're receiving more electrons. Those electrons are not scattering so much, you're receiving more power as you get closer to it. Now if you notice, I was holding this dipole vertically, and Larry's holding the rubber duck antenna that's on here vertically. Now if we put them in the same plane, it's going to light up similarly. And if we turn that, it starts to go out. Can you see as he gets back closer to it and they're parallel, it's brightest. If they're perpendicular, it's dimmer. It's still lit when we're perpendicular, but it is very, very hard to see. And that's even this close to it. But as we turn back parallel to it, then we get it. So this is what we know of as the orientation. Are you vertically or horizontally polarized? And so when you hear about people that are cross-polarized, well, I'm transmitting vertical and you're horizontal, that can be a problem, particularly at these frequencies, VHF, UHF. When you get down into the HF bands, then that's going to then be less of an issue because it scatters around a whole lot more. But you want to be on the same plane or the same orientation as the transmitter, and you want the transmitter and the receiver the same polarization. Interestingly enough, has anyone noticed the orientation, the polarization of the antenna on your automobile? On your car, how's the antenna? It's sticking straight up off the hood, right? It's kind of sticking up vertically. Well, that's because it's easy to put that on a car vertically. That's why all of the FM radio stations that you may listen to in your car are vertically polarized, is to match the vertical polarization of most of the automobiles. So we've got this kind of polarization and the distance that's on here. That's with an omnidirectional antenna. Now this omnidirectional antenna is transmitting basically what you would imagine as a donut. We've got our ring of signal strength coming out here, and it's kind of irradiating in circles. I like to talk about how it's similar to a pebble in a pond. You got a real smooth pond in the morning. You go out there and you throw something, or maybe a fish jumps, bloop, and then you start to get those concentric rings, right? That's kind of like a transmitter exciting the radio waves. Imagine if you got out there with a plunger or something on that smooth water and you could plunge and push and make a lot of waves that way, then you can create a lot of waves. So what we've got here, you got it?
You got one too many.
Here you go. Here.
Adapters.
Yep. Flexibility.
I grabbed the wrong end.
And put that on there. Okay, I'll hold this. So what we've got here is, this is a Yagi antenna. This is one that we use handheld for working satellites. You may have seen these. Here at Hamvention 2019, Arrow Antennas is here. It's not a plug, I'm just a fan. Basically we have the same thing. We have a 70 centimeter dipole. I was just showing you the light bulb. That's basically what we have right here, is a 70 centimeter dipole, but instead of using some copper wire, we now have aluminum arrow shafts on here. I'm going to take these elements off because I'm not going to use them. They're going to get in our way. These are the 2 meter elements. These are 2 meter dipole lengths, roundabout in that neighborhood. And we're just going to put them over there, get them out of the way, step on them later. There we go. All right. So now what we're left with is a 70 centimeter or a 440 Yagi antenna. Now there's a lot of elements on here. I'm going to quiz you. What are the names of these? So we have this one where the feed line goes into. Do you remember what the name of this element is? This is the driven element. It's where the signal comes in and it's driving. That's where the signal, that's what's creating the waves. Now behind it, we have the reflector, and in front of it we have the directors or the directors. So you reflect the signals here, and the directors help channel the signals in one plane there. So I'm going to do this one further. I'm going to strip this thing down a little bit more, and we're going to add these back in a little while. But I'm going to take the whole front section of this thing off. So we have just a short, stubby, 70 centimeter antenna. And I'm also going to take off this very back element here, the reflector. So Larry is back to his plain Jane dipole. And he's holding that dipole. You're still on 436,790?
Well, 436,815.
Okay, close enough.
Close enough.
Um, so we're going to use the that particular frequency, and he's going to transmit that signal. Now this is a dipole, it's omnidirectional. And if I hold this in that plane as I come in closer, if you notice, this is lighting up just a little bit out here, and it is a little bit further away than we were with that rubber duck, right? That's because this antenna is a little bit more efficient than that coil of wire that's inside the rubber antenna. Now as I bring it in closer, you can see that it lights up quite a bit more. Again, it's more efficient. And if I rotate this one out of the same polarization, then you see that it's dimmer. We bring it back in. So we've got that, and if I rotate it around, all the way around here, it's lit up no matter where I go. So that shows that we're omnidirectional. It doesn't matter if I'm forward, backward, left, right, it's going to light up on there. So the next thing I want to do is I'm going to come in and I'm going to add in that reflector. We're going to reflect the signal so that we don't need the signal going back to Larry. He's the one transmitting, right? So we're going to put that one through, hold that one on. Now we're going to just try that one. We're going to key it up. All right, so we're going to bring it in. Whoa, look at this. We're already lighting up out here. There we go. So we've got it over here, and if I bring it out in front, it's not nearly as bright as it is over here. That's because all of the radio energy that was going back towards Larry is now coming out this way. So we've got a little bit more of a lobe coming out here. And if I bring it around the back side, it's still lit up over here because we still have that kind of a dipole effect. But if we bring it out here, it's kind of a dipole with a lobe over on this end. What's that?
How about in the null?
Oh, in the null. Okay, so yeah, so we've got it lit up out here. Bring it around the back side here. Well, if it lights up this far, it's like, kind of about yay far there. If I bring it back here, same distance away, more or less, but it's not lit up. And it's not until I get back over on this side. So that reflector is pushing out that way. We're going to put this one on. This is one of our directors. Not a division director, mind you. ARRL joke. All right, so now we've got our reflector and we've got one director. What should we have? We should get a stronger lobe towards me and not as strong towards Larry. So I'm going to start it off to the side here, transmitting, bring it in close. We still got a little bit of that dipole effect, but I'm having to get a little bit closer now over here. If I bring it towards Larry, well, it goes out really quick this way. And that's because this is kind of pulling, the director is pulling the signal this way. And if I come out over here, it's still really strong. Wow. Look how far out I can get. It's still lit up over here. I know it's kind of hard to see, but it's still lit up to this point right here. Wow, remember that original dipole I had been really close. All right, so Larry, if you would take that one off, let's put all these guys on here. We're going to just go for the whole shooting match here. So this one we've got multiple elements on here. Put that one in there, lock it in place. We put that one back through to hold the two pieces together. There we go. Perfect. Okay, now stand back, right? Because I don't like 5 watts. So, all right, so he is transmitting now. Let's see, we're going to walk it in, walk it in, walk it in. It's just starting to glow at this distance. Now remember, it's not just from here to the front of the Yagi at this distance. We're going back to the direct element. That's where the signal is actually propagating from. It's just bringing it out this far, and it's just starting to glow at this point. If I come in closer and closer and closer, it gets brighter and brighter. Now, of course, if I get in closer, I can get it very, very bright. The difficulty there is the light bulb can only handle so much voltage before it goes pop. So we want to preserve and save the life of the light bulb without going too close in here. But let's bring it around to the side of the Yagi. And you can see that as I get it back over here towards the driven element, it's still lit. But if I get back towards Larry, it's off really, really quick behind it. So there's more of the signal going out towards the front. It appears to be pulling the signal from the directors, and it's going away from the reflector. So as it gets to the reflector here, it's completely off. and then it starts to light up. So it's really, really strong all the way out to this point and beyond. Now this antenna is used quite a bit for satellite communications. That happens to be why I'm on the frequencies that I'm on. Satellites being a couple hundred miles away from us at any one point can be difficult to reach at that point, so we have to send a signal really far away. Fortunately also that our radios are more efficient than light bulbs are, and so you can hear that signal a little bit more close in. So that's an example of using elements that can direct your signal, and the way that the light bulb can show how gain operates and different patterns that it's on there. Because usually you'll see that like in a manual or something, it shows the pattern on a piece of paper, but that seems a little abstract because it's just like, well, that's textbook, but how do I see it in real life? And that's what I like about having the Yagi antenna there. Some other fun that we can have with magnets, I'm going to actually let Larry talk about this one. This is a great little project that we do at the Teachers Institute. I'm going to, you want me to prop it up here on this laptop?
I can hold it.
You don't hold it? Okay.
It's easier to control that way. This is usually kind of talk about this following the magnet and tube demo, and basically a DC motor. Parts are dirt cheap, D-cell, cheap magnet, a couple paper clips, piece of enameled wire. And you can either use a rubber band like I did here, you can use black electrical tape to bind it all together. And you know, it's not particular exactly how much wire, how many turns you use. I just wind the wire. I usually use, for something like this, I'll take 5-6 feet of wire. Wrap it around the D-cell, leave about 3-4 inches pigtails on the two sides, and wrap it around the coil at 180 degrees apart from each other. The trick is, in order to kind of create the commutator effect on the motor, you need to sand the enamel off, sand the insulation off one half all the way around, all 360 degrees. The other side, of the rotor, you need to sand off just 180 degrees of it, half of it. And so that at the point where the two bare parts of the wire are touching the paper clips, you're basically magnetizing the coil, and the coil is going to turn towards the permanent magnet. Now it's got some momentum, so it's going to go past the strip part of the wire to the insulated part of the wire. Now it's not magnetized anymore, but that momentum keeps it going. And back to the bare parts of the wire, it's remagnetized, and it's just sort of giving it a little magnetic kick. That's the basics of how a DC motor works. There are lots of homopolar motors. You might have seen those on the internet. This is a little easier to kind of understand how it works than a homopolar motor. It's not. Some of those are even simpler looking than this, and they're neat and they're cool. But this kind of ties in with that. It says, okay, how do we take that effect and do something useful with it? So, and it will run off a D-cell. How long has it been? It's about 2 days off a fresh D-cell. 2 8-hour days. And the secret is really just getting it balanced so that it's not cranking one way or the other, but it's just sort of sitting there like that. You can set it on a table and it'll just go and go and go and go.
So the key thing, like you said, the key important thing is to sand only half of one of those wires, so that it's insulated on that one side. Sometimes people will make these and then they'll contact and be like, "Why isn't this turning? It's getting really warm, but it's not turning." And it's just because they're shorting it out.
It's attracted to the magnet like it seems like it ought to be, but it's not turning. Just sitting there pulling over one way. Now, in our Teachers Institutes, the teachers receive a USB oscilloscope that they hook up to a laptop. You can hook up that USB oscilloscope to the two paper clips and basically look at a square wave, okay, that this is putting out. You can directly measure the RPM of the motor doing that. So you can have contests to see who can build the fastest motor, things like that. And if you're a teacher, you want something for those kids that are kind of smart alecky that get it done really fast. So you give them a AA battery and say, okay, now build one with thinner gauge wire usually. Okay, build one for this, smaller paper clips, same magnet.
Different varying sizes of diameter on the ring.
I've got a whole list on the back of our little description sheet for this of 20 different ideas of things that you can do with it, experiments you can try, things you can vary. So it's just a silly little experimental test bed. It makes a great demo. At our booth, for some reason, it's the thing that everybody stops and cocks at, So
it's just a little bit of motion. It catches the eye.
Yeah.
If you want to build some of those, if you go to arrl.org/ETP, it's the Education Technology Program, we'll have links embedded in there to the PDF that Larry built for the directions for that, and also for the magnet pipe.
The tubes, yeah.
Yep. So that's kind of lists out the stuff that you need there. Again, that's arrl.org/ETP.
We'll probably eventually have some of this other stuff written up and available there as well.
So the other thing we wanted to show off is with the ETP, we've got the Teachers Institute program. And the Teachers Institute program, like I said, it's donation based. It doesn't come out of general ARRL funds, and it's people that are feel a passion to have teachers integrate this kind of content in their classroom, in their science, math, or technology classrooms. So what I've got here, I'm holding, this is a relatively new robot. This is one like what we use in the Teachers Institute. This one's called the Cyberbot. It's by Parallax. It's a joint effort between my personal employer, NYSERC, the National Integrated Cyber Education Research Center, and Parallax, the robotics company. This uses the microbit brain to program to control this robot. In the Teachers Institute, we are using the Arduino on the ShieldBot, also from Parallax, and historically we've used the BowBot, which is the basic stamp. The concepts are all the same, and that's really what we're after as educators. We don't care about necessarily which platform we're using as long as it's instructionally solid, it covers the content that we need, but what we're after are the learning principles. Now also as classroom teachers, we're looking at, well, what's engaging to the student, to the kids, and what are they after? And we know that robots are exciting to kids. There's even a group here at Hamvention 2019 that are showing off their robots. This is a much smaller version of what they've got, but the principles are the same. So we've got a board up here that's a microcontroller we can program, and then on the bottom we've got a couple of little motors here. These are servo motors that we can control the speed of, and then some AA batteries. So this little guy will drive around. This is the front, and then this is the back here. We can write code to this and tell it to turn those motors. But the great thing about this platform is that sometimes the robots drive forward, and then the students the robot just drives forward. But what does that mean? What's actually happening when we say just go forward? That's a lot to process. Similarly with humans, if I say I'm just going to walk forward, what happens when you walk forward? Well, subconsciously there's a lot going on. Your muscles are moving to pick up your leg, move it forward, set it down, shift your weight, pick it up, move it, set it down, shift your weight, and hopefully you walk a little bit smoother than just those few actions, right? Hopefully you can move without having to think about each individual step along the way. The same thing happens with the robot. The robot needs to be told exactly each little step, and that's why we come up with what we think of as robotic motion. It looked really robotic the way they were walking. It's because it's not a whole lot of fluidity in the movement there. So we use the robot to program this. What does programming have anything to do with ham radio? Well, what we do with this on the Teachers Institute is we introduce basic electronic components. We get into some soldering. The students actually build 24-hour clock kits. The students are teachers in the workshop. They're putting together these little 24-hour clock kits that we've had designed. And then the programming side of it comes in so that we can turn on and off different circuits that we build on a little breadboarding area. So for a lot of our teachers that attend, this is the first time they've ever done anything with any kind of breadboarding, any kind of electronic components they've built circuits with. But before it's all said and done, they're able to build and discuss and describe circuits on the breadboard with ease, and we don't have to think about each individual component. They're not having to, the first time we build something, they're having to count holes, and they think that it has to be exactly just this little piece right there, and what color LED should we be using, these kind of questions. But eventually it's like, okay, just build an LED circuit. And they know, okay, well, I'm just going to get this kind of value resistor and this value LED and put that on there. They can do that, and then we can write code to control that. There's a lot of further exploration you can do with that, kit building, and you can do other kind of circuits on here to detect motion. A lot of that can go in there. And people will usually come up and say, yeah, but again, what does robots and programming have to do with ham radio? Well, for our target audience, teachers, and you doing this in schools, I like to say this is kind of ham radio through the back door. If we come in there and kick in the door and say, hey, it's ham radio time, a lot of kids are like, I don't have any idea what you're talking about. A lot of teachers don't have any idea what we're talking about. But this is something kind of similar. This gives them some context for it. And what I like about this is something that's cool and engaging and fun to kids. It gets some electronics concepts through their heads. It gives us some empowerment that, hey, I can build stuff and make stuff and create my own solutions. And then what we got is we go from that stage to, now I want you to drive it across the floor here. I want to drive around the room. I want to drive across the parking lot. At some point you want to drive your robot further than you can reach or that you can control. And that's when I like to talk about bringing in APRS. And APRS, what's that? Well, you can bring in ham radio for that. We've got a mode called APRS, and usually by that point, they've already steered clear of what the original application was. Can we use APRS to control robots? Yeah. And then by the time they try and explore all the components of that, they're hooked into ham radio at that point. And then they want to explore all the bazillion different corners of the hobby and the niches that we've got within the hobby that they can have fun with. They can take part in Skywarn exercises. Every kid likes to be the hero, so every kind of severe inclement weather that we've got at back in my home state of Texas, kids want to get their ham radio license so they can peek out the window and they can help with the Skywarn. And it's like, kids, that's something you can definitely help with. Adults need your help with this. It's not just lip service. Like, we actually need more spotters out there. So that's one way that robotics can use that.
We also talk about signals. Don't mean to jump over anything you might be getting ready to talk about. We also talk about signals and signal processing. Okay, and so the whole idea of DSP, digital signal processing. What is a digital signal? What's an analog signal? What does digital signal processing do to that digital signal, and so on?
It seems really abstract when we start.
Introduce those in a real concrete way with this platform.
Yeah, so we've got on here. I mentioned those motors that are on the bottom. These little servos. They operate off of pulse width modulation. And I love whenever the teachers at the end of these workshops say, I know how to do pulse width modulation. It sounds really technical, and maybe it is, but it's approachable whenever you're using it in this context. It's something that you can master and it makes sense to you then. At first it seems really confusing, but all you're doing is you're controlling how long the so a voltage is turned on for, and if you look at that on an oscilloscope, it's the width of that pulse, and that width of that pulse carries some information. In electronics and in radio, we say that when you're carrying information, that's modulating information on some kind of line. So we have the width of the pulse telling the servo how long or in which direction it should be turning. So the width of the pulse carries information, so it's pulse width modulation. Code is in there for it, but they have to tell the motors how many milliseconds it should be, or how many microseconds it should be running for, sending these different pulses. That tells the wheels to turn forward or backward. Catch is, these motors don't know forward and backward. They know two directions. They know clockwise and counterclockwise. So your pulses could change that. So what do you mean there's no forward and backward? It's clearly forward, right? Well, if I turn it this way, that's going clockwise on this wheel to have it driving forward. If you look at the other wheel back on this side, remember we're going to be going forward, this is the forward. If it's turning this way, this is going counterclockwise. So in order to go forward, you have to turn the motors opposing directions. And in that, it gets kind of weird until you start looking at it, it makes sense. Well, then you have to tell the servos different signals on there, and so you have to kind of come to terms with that pulse width modulation early on. We take that, we put it onto an oscilloscope on the computer with teachers, explaining what an oscilloscope looks like, and it's a great way to look at the signals, make sense of code that you're controlling, and then look at the signals on a screen, and that has some meaning. Am I turning this clockwise or counterclockwise? The other thing that I like about teaching programming and with microcontrollers such as the Arduino, it puts you in the driver's seat. So, you know what would be nice? If someone made a thing for amateur radio that does whatever. Now, if you know how to program, not a problem. It's like, well, I could go out to the flea market next time at Hamvention, and I can definitely find the parts to do this and this and this, but how am I going to control them? Well, if you're just an introductory hobbyist, you get into it with an Arduino, that can turn those things on and off at the right sequence. I have friends that are making interconnect boxes for radios in a multi-station setup, satellite controllers that aim satellite rotators to track satellites with something like the Arrow. Lots of different applications you can do with just a little bit of programming. If you've never programmed before, it seems daunting, and I think that everything for the first time seems daunting the first time. The first time we came here to Xenia, to Hamvention, you remember that when we came from Hera and we moved over here? It was like, where is everything? We're happened to be in Forum 2, right? You're probably still lost trying to find, where's Forum 2? You're asking around, where's Forum 2? The first time you get into something, it seems difficult. Programming seems difficult. And maybe it is, but, and I haven't asked any of them, do you think a heart surgeon or a rocket scientist goes into work every day, kicks in the double doors and says, behold, I am a heart surgeon, or I am a rocket scientist, this is rocket science, it is hard. No, they're comfortable with it. They know it. They don't sweat it. They know it. Maybe the first time they got into some of the courses may have been hard for them to get into that. But they know it and they know it well. Same thing with amateur radio. Is amateur radio hard to you today? No, but maybe when you're first getting your license, it seemed, well, I'm never going to remember all this stuff. All the questions they asked me on this novice exam, it's never going to fit in my head. I'm never going to master code. I'm never going to get my technician license. It's too hard. That's just because it's the first time. And same thing with programming. It's always kind of stretching your brain, teaching you a little bit more, and when you know a little bit more, you can learn a little bit more. And if you know a little bit more, you can learn a little bit more, and you can just amass knowledge that way. It's one of the beauties, I think, of amateur radio is that you can continue learning all the way through the hobby. You'll never master it all. You know that guy at your club that says he knows it all? He doesn't, right? So that's the fun of amateur radio, is that you're always learning. There's always something around the corners. You know, what's next, what's new. We're always adding on. Even the old stuff, you can't master all of that. The new stuff, you're never going to master it all. Take joy in that you're never going to run out of stuff to learn about. That's the fun part. That's what we do in the Teaching Institute, teaching some of this stuff, bringing in different concepts that
Changes every year.
Yeah, we're changing stuff all the time. Amateur radio changes all the time, and we're always kind of showing different concepts and how you can approach the stuff that may seem complex, abstract, or different. So we'll have all the toys up here if you want to come look at it when we're done here in just a moment. But we thank you for your time. Again, Tommy Gober, N5DUX.
Larry Kendall, K6NDL.
Thanks a lot, guys.
Thanks for coming. By the way, Tommy only scratched the surface, so.
Yeah.